In this video, I want to talk about how much heat is required to raise the temperature of a gas. Flashback. Remember we had Q equals mc delta T. We're going to try and basically upgrade that formula to handle gases. I kind of glossed over gases in that chapter and we just kind of just hand waved it. But the techniques we use for gases are a little bit more involved. So let's get to it. First off, we usually want to specify which type of process. Do you have a constant pressure process or a constant volume process? And I've got a visual aid here just to really drive this home. We'll come back to this one. And this, we'll get this out of the way here for a second. All right, so in this case, I've got some boiling water here. You can see the steam going. Now, in this situation, we've got two scenarios here. We have a sealed vessel, all right? That's a constant volume process. I could heat this at constant volume. Now, I want to be careful here. If I stick this in here, the pressure is going to build up and this could explode off the top. I don't want to do this for too long, so I'm not going to. Now, here I have a constant pressure process. Let me get this set up. All right, so right now, that piston in there is being supported by the air in this, and so as I heat this up, I see the volume changing, but the pressure, which is determined by how much weight I put on here, is remaining constant. Obviously, you can do a constant pressure cooling process. But so we heated the gas, and we can change the volume while keeping the pressure constant. And so that's one way to think about it. A classic way in chemistry class, maybe you think about, let's get back to the board here. In theory, you could imagine just leaving the container open and having atmospheric pressure up here. That is a constant pressure process as well, but watch out. If you have a lot of the molecules evaporating, then the number of moles is changing. This will be a complicated problem. So, but yeah, basically, if you have a piston in the problem that can adjust its position, that will give you a constant pressure process. If you have a sealed container, you're going to have a constant volume. The name of these: isobaric process, isovolumetric process. And if you don't like saying that long word, another phrase is isochoric. Okay. Now, another difference here: C sub P. I'm trying to just these serif on here just to indicate that's a capital C, not a lowercase c. So notice we used to use Q equals m lowercase c delta T. This is going to be a capital C with a subscript. It's not heat capacity. This is just the style I've seen written in many books. So this thing is called the molar specific heat at constant pressure. So notice the units, right? This one is going to be in joules. This is mole. This is CP. And delta T. So the units on this thing end up being joules per mole Kelvin, not per kilogram Kelvin. All right, so there's that. Similar units for this one, but notice there's a subtle difference between these two. There's this symbol F, all right? F is called the degrees of freedom. And that's true for both of these sides. What does that mean? Well, I've got a whole whiteboard to explain this. Let's go to board 2. All right. So most of the gases that we're going to deal with in this class, I guess I could turn this heat source off so it's not just wasting energy. We're usually going to use monatomic gases or diatomic gases. Monatomic being things like ideal gas was the old phrase, inert gas was a phrase, noble gas was a phrase, argon, helium, neon, things where a molecule is a single atom, monatomic. Okay, monatomic gas means one molecule. So it's basically like a baseball or a softball here, right? And we say it has 3 degrees of freedom. It can move along the x-axis, y-axis, or z-axis, right? X, y, or z out of the page. And so those are the 3 degrees of freedom. It's free to move in 3 dimensions. Things get a little bit more complicated. Just making sure you can read this, okay? When you have a diatomic gas, and that's what this screwball looking thing is for. All right? So, and the short version is, it depends on the temperature range. There's low temp, medium temp, and high temp. And we're going to use these results and go with it. Now, you'll notice there's kind of this gap in between here, between 80 Kelvin and 200. Now, that's because of statistics and thermodynamics, and let's just gloss over that. All right? So let me just try and describe this. At low temperature, there's not enough energy to cause this thing to vibrate. This is a very stiff spring, and it's not going to rotate much like this. So we're not going to have enough energy to rotate it or oscillate it. So it's literally just moving around like a monatomic gas. There's 3 degrees of freedom. It can move along the x, y, or z axis. As you heat it up, you can actually start to have rotation like this or like this. Now notice, rotation like this is basically negligible contribution. Why? The moment of inertia of this for a molecule is essentially 0, right? Ixx, or the moment of inertia about the x-axis. Why? Because all of the mass is on the x-axis. You know, you're saying, well, what about the atoms? Remember, most of the mass of the atom is in the nucleus, which is 10 to the minus 15th meters. So the mass is 10 to the minus 15th meters from the axis, versus a molecule could be spread out by maybe nanometers. So this rotation is completely negligible compared to this one or this one. All right, and so in these temperature ranges, ding, 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 notice room temperature is in there. Most of your engine problems that involve gas is in this situation. If you're trying to understand a gasoline engine that uses air, which is mostly nitrogen and oxygen, or maybe you add some fuel to it, but whatever. So we're probably going to be using F equals 5 a lot for these problems when we do engine problems. Anyways, all right, great. And now eventually you can add in vibration. And the short version is you can have symmetric or anti-symmetric vibrations. Who cares about that? Just know that if you're at really high temperatures, this ramps up to 2000. So how do the degrees of freedom change? Read a book and you'll see there's a plot. If you needed a specific number of degrees of freedom, you could look it up. I think that's enough on this. But I do want to remind you that what was the point of this? C sub p was F plus 2 over 2 times R. That's your 8.314 joules per mole Kelvin. And constant volume specific heat, molar, was F over 2 times R. And so if we want to understand how much heat is required, we then use Q equals NC delta T, and you plug in either C sub P or C sub V. And how do you figure that out? Usually you have to know the temperature range you're involved in, get the degrees of freedom, shove that in, stick this in, know the number of moles, you can calculate something.